Hi, I'm Heidi Legg with TheEditorial.com. Today we are interviewing Dr. George Church. He's the Robert Winthrop Professor of Genetics at Harvard University. George has the largest lab at Harvard, and I think that says something. George, what drew you to genomics, and was this something you knew very early on was an interest?
Maybe not genomics, but anything that involved mixing biology and computers and math was really, it was something I was looking for, but not finding immediately. But from very early age, I was looking for things like that. My dad was a physician, so I was interested in how he got the technology that he used. I wasn't really that interested in becoming a physician. And there were bugs in the backyard, and there were, computer just seemed really interesting. And it took me a while to find the mix. And one of the first mix was crystallography, and the second mix was genomics.
Now, you grew up down south,
Yeah.
and often we hear stories of people who we consider visionaries like you, which we do, have their parents could see things early on. Does your mom or dad tell stories of things you used to play with or things that you used to do as a kid that sort of showed that you were going to have this sort of disposition?
I don't know if my mom and dad tell the stories. They passed on quite a while ago, and I left home when I was about 13 or so. But I think I would definitely. I tended to build things. Some of my friends and brothers would take things apart. I would try to build little analog computers and models and things.
13's a young age to leave home. Where were you going?
I just went away to a boarding school up here in Massachusetts, so it was a culture shock going from the south to the north, yeah.
And have you left Massachusetts at all in that time?
Since then? Well, since '68, yeah, I've lived quite a few places, including San Francisco and North Carolina.
And what's drawn you back to Boston to do the research you're doing?
Well, it's an amazing student community. Harvard and MIT, you just don't get much better than that. And also entrepreneurial, at least something I discovered in the 70s was that Boston was already getting pretty good at entrepreneurial back then. I certainly enjoyed personally the feeling of technology development and genetics, genomics, sequencing from about 77. Actually, when I started graduate school, it seemed like we were onto something.
What did you notice? What were some things on the landscape that you sort of were indicators?
I had worked in crystallography where a lot of things were automated. It was really the only field of biology and probably chemistry that was fully automated. You could stick a crystal into this device and it would just in the dark without, just rotate around 3 axes and collect all this data. And it was this beautiful dance. It was kind of before people were really thinking about robots. It wasn't really, but it would do this little dance for days on end. And I thought, that's really cool. Can we apply that to other fields of biology? And genomics was one of the first that we tried. And I happened to land in Wally Gilbert's lab, who, wasn't complete once I applied to Wally Gilbert's lab, but and he was onto something in terms of inventing DNA sequencing, and then I just put the two together, which was if there were ways that you could automate it, and by automate, sometimes you have to change it completely. You can't really take it the way it was.
What is the Personal Genome Project?
Right. Yeah. So the Personal Genome Project is the only source in the world that we know of where you can get open access to genes, environments, and traits for human beings. There's lots of freely accessible information about animals, plants, but for humans, this is a unique resource, and it really enables all kinds of studies like being able to share stem cells where you know the genome sequence and you know a lot about the person, and you can test out gene therapies, you can test out drugs, you can test out a lot of ideas in these kind of shared resources.
And who's able to access it, and do they have to pay for it?
So it's free. Anybody in the world can access it. You don't have to prove that you're a researcher. Sometimes there's a fine line between a researcher and a student and somebody that just happens to have a computer. It's very hard to judge who's going to make fundamental. In fact, some of the most out-of-the-box thinkers are the least credentialed people on the planet. They've been rejected in one way or another, but they still have a lot to offer to society. Yeah.
There seems to be a tension and a conflict between raw data and findings. Why is that? And can you explain that to all of us?
I think this is contentious and discussed. I think it may look like a tempest in teapot when we look at it back from the future. The raw data is kind of like if I give you my blood, or if I fill out a form where I fill in, what I think all my diseases are. That's raw data, and I gave it to you, and now you should be able to process and give it back to me. In other words, you should say, this is what I have in my files, is it still correct? And I can look at it and say, yes, it's still correct. Or you can process it even more and interpret it slightly and give it back to me. Does these interpretations ring any bells? And I can say, well, now it's getting a little technical. Can I get a second opinion, right? Or, hey, it's starting to sound like this could impact my health. Can I get a second opinion? Because you just want to do a research on it, but since we're sharing here my data, why don't you allow me to get a second opinion? So that's why I think people should have access to both the raw data, some of which comes from them, and the interpreted data, so they can check it for errors, check it for things that don't make sense, and possibly check it with other experts to keep the whole system more honest and possibly benefit.
When you and I first met, I remember clearly that I said to you something along the lines like, does everybody really want to know their sequence? They really want to know how they're going to die or what's wrong with their... And you said, well, people should know about it. Can you talk to me about why you believe it's better to know?
I don't think everybody should know, capital S. I think it's a lot of people do want to know, and a lot of people don't yet know enough about it to make a decision. But they could know, right? Today, they could know. They could have enough information. And the point is not to know how you're going to die. It's to know how can you avoid premature death, premature disability, premature senescence, all sorts of things that if there's something actionable, predictable and actionable, then I think a lot of people would want that. I think they get confused by the typical press coverage, which is, genetics is not informative, or if it's informative, there's nothing you can do about it. I mean, I think there's just tons of genetics that is informative in it and about which you can do something.
What gets you really excited about the work you're doing? Things that you can change, cure?
Well, so, it's very exciting that we can now deal with roughly 2,000 different genetic diseases that are highly heritable. Typically, they're not cured. You can use genetic counseling as a preventative. But genetic counseling are things that are preventative, and they involve reproductive decision making, and in some cases, preventative surgery like cancer. There's another set of preventatives, which is public health and reducing environmental risks. A huge environmental risk, especially in developing nations, is infectious disease and the vectors, the mosquitoes and ticks and flies that carry them. And malaria is one of the big ones, with 600,000 people per year dying of it. And one of the new things that we're just started working on, although its roots are back to 2003 with Austin Burke, is called gene drives, or CRISPR gene drives, or RNA-guided gene drives. So basically, you can put a payload into a mosquito, as little as one mosquito, although you might do more, that says this mosquito is resistant to malaria, and every time it mates, all of its offspring will have the same cassette in the same position of that same chromosome in all of the offspring. So you might have 100 baby mosquitoes, and then a few weeks later, they will all mate and have 100 each, and it spreads exponentially through the population, starting with one designed mosquito. And it's It's inexpensive because you don't have to go and inject every mosquito in the wild.
It's amazing.
You don't have to vaccinate every single person in the wild. It basically does it itself. But there are a lot of discussions we have to have about how to do this safely, how to test it in the laboratory. But I think that's going to be pretty awesome.
Colbert jokes about how you're creating a squid man in your lab, or the potential for it. Is there anybody who is actually auditing or creating limits around this type of genetic development?
I have encouraged limits, that is to say, and not just voluntary. I mean, I've encouraged discussions. Ours is one of the few, biotech technology developing groups in academia that also does, kind of active innovation in bioethics. So we have full-time bioethicists, Jantine Lonsoff, and there are innovations that you can have. So it can have surveillance of synthetic DNA to see if people are asking to manufacture things that they're not equipped to handle or haven't documented what they want to do with it. So select agents and so forth. That was one of the 2004 suggestions. The Personal Genome Project is a bioethics strategy for dealing with privacy concerns. We have around the gene drives. The first 3 papers we did were all cautionary about how to do it in a way that's reversible or monitored and so forth.
But you can't really stop that. If someone can get this technology, is it a very small group of you that are this advanced?
I think that if you say you can't stop it, then it becomes much more likely you can't stop it. But if you do everything you can get a virtuous cycle that gets people more and more excited about doing things the right way. And that you build a culture, so you can have, in the robotics world, you have the culture of robot wars. That's how they intentionally, the initiators, the entrepreneurs, felt that was a good way to train the next generation. Well, in synthetic biology, we've gone the other direction, where we've asked for human practices and very considerate and transparent discussions. And surveillance goes beyond transparency. Transparency is often voluntary, or it has a component of cooperation involved. But with surveillance, you can try to be more and more invasive into, if you're a synthetic biologist or have any synthetic biology training, there's absolutely no reason why you should have any privacy. Nobody forced you to become a synthetic biologist, and so you should acknowledge that everything you do on and offline is going to be looked at very deeply.
Is there a very small group of you? When I spoke to Keith Flaherty, who leads all the targeted therapy for cancer over at MGH, he said we're a pretty small group that's in contact around the world doing what we're doing. Do you feel the same way about the people that you're working with around the world?
Well, most of there are, you could get the feeling that you know everybody.
Do you all get together once a year, twice a year? Do you email each other?
But again, it's a feeling. So you get together, there's a limited number of meetings. You can't make all of them, but you make enough of them that but there's always edges. So especially with do-it-yourself biology taking off, there's a lot of edges there. There's companies and governments and military, and so there's these corner cases that you need to deal with in terms of surveillance, in terms of bioethics, and so on.
Does it stress you out?
I would say it encourages me to be vocal about communicating the risks and the benefits and how we can work together to encourage the innovation on surveillance and safety and security.
There's sort of 2 metaphors out there on how genetics are working with the public. One being the bank relationship, where you'd like it to be, where you give something to the bank and they give you something back, and that's your Human Genome Project. The other that I felt was related to this was the Catholic Church. It used to be that no one could understand the Latin but the priests. Can you tell us how that's changing and why it's important to you?
I'm not sure I don't know the context of the bank analogy, but I think with the liturgy or the religious texts, the breakthrough was the Gutenberg Bible that made it available in print rather than just illustrated manuscripts, and then the translation into common languages made it available to people in general. So that concept of education of the masses rather than the priesthood, I think, was very important. So I think we're more analogous to Wikipedia. It's not that you make a deposit and you take something back. Well, in Wikipedia, you can edit the articles if you have something to contribute. Other people will check to make sure that you edited it correctly. But then you take out of it is you can, anytime you want information that's fairly well vetted, you have a resource, and that's what we're trying to do. There was a time where most of encyclopedic type information, even post-Gutenberg, were in these silos of proprietary books, and then Wikipedia completely changed that. And if I were today trying to put genetic information in little silos and protecting them the way we used to protect encyclopedias, I would be looking over my shoulder at the Wikipedia version, which is Personal Genome Project, or contributing to it and making it better.
I gave my dad for Father's Day a few years ago the 23andMe kit, and we had him spit in the test, and we were all excited to see what was going to come back.
Yeah.
We couldn't really understand much.
Yeah.
And so that's why I keep revisiting this point of how do we participate? How do we get to be part of this amazing stuff you guys are doing and understand and use it?
So here the analogy, so Wikipedia is the analogy for sharing. The analogy for understanding, I think, is global positioning satellites. Global positioning satellites, very complex technology, large-scale integrated circuits, thrust up into the sky with Newton and Einstein, and then precise timing and atomic clocks. You don't need to worry about that. When you pull out your phone, you just ask, am I turning left or right? right? And so the key to understanding isn't understanding every single thing in the world at the atomic or subatomic level. It's having great software. Because that's how you can relate to it. People understand weather. Part of the reason they're fascinated with stars is they used it for celestial navigation. Now we actually understand stars less than we used to, not more.
Right.
Because we don't need it for navigation anymore. But we understand GPS a little bit better than we used to, right? And other satellite things. So I think it's really you understand as much as you need in order to make technical decisions, like which cell phone to get, and whether to vote for global warming or not, and that sort of thing. And that's what we need to do with that's what we are doing with genetics. I mean, you can get not just 23andMe, which is just a few SNPs, and it's mainly aimed at ancestry at this point, but you can get your whole genome sequence, and you can find out if there's anything actionable. And if there isn't, that's very easy to understand. Nothing to do right now. Come back a few months and see if it's changed. But if there is something to do, then the understanding will be take this slip of paper to a physician and ask for this test. I think we should keep the bar high, that's fine, but I still think everybody should get sequenced, because that information, if it's accompanied by a pretty simple preliminary test that shows you know what you're getting into, that you're not going to freak out no matter what you see, right? You're going to follow up calmly. If you can't sign that, then you shouldn't get the test. But if you can sign that, then everybody should get the test.
Do you believe?
And I think basically everybody can figure that out.
Do you believe most people can handle it?
I think with a little education, yes. I mean, it's not any harder to handle than, you have high blood pressure, or your kid has phenylketonuria, you have to keep them away from phenylalanine. We're handling lots of medical, including genetic information already. It's just, for some reason that people convince themselves that genetics is a little special and isn't here yet, when it's just as here as other medical things.
Who's holding you back from all of us being able to get tested?
Well, I think until recently the cost was holding them, and maybe still the cost. The cost should keep coming down. When I first started talking about the $1,000 genome, the genome was just starting to come in at $3 billion, and it just seemed laughable. And now it seems like it's not low enough. And in fact, almost immediately, as soon as I said 1,000, I said, nah, it really should be 100. And eventually it will get to the point where if everybody's reimbursed to some extent to the end user, it's free, and that will encourage people to do it. Won't necessarily, it could lower medical costs overall because if people are avoiding taking the wrong drug, which costs money, having the things that go wrong when you take the wrong drug or the wrong food or wrong
Why
surgery.
not have it? If you can have it, why not know? It's sort of
Right. I mean, all the software and all the counseling has to be set up to use that information to bring down medical costs and to improve quality of life. I think we could even tolerate a little increase in medical costs, but my guess is it will actually come down.
How do our insurance companies reacting to this? And should I be worried by giving my genome that insurers are then going to charge me more? Or?
Well, in the United States, it's against the law for them to charge you more based on your genetics. So the Genetic Information Act of 2008, Genetics Information Non-Discrimination Act of 2008, made it illegal for employers and healthcare insurance companies to discriminate. You can still get discrimination based on long-term care and life insurance in the military, but I think for the most part, there are very few examples of it, even before the law. I think what we really want to do is encourage them to not discourage them from using it, not only discourage them from discriminating, but encourage them using it for good. I mean, I think that's the thing is, don't get insurance companies freaking out that this information isn't good for anything. It can bring down in principle, it could make insurance more profitable.
Do you feel like you have a lot of allies in the sort of business world and government that can help you get us to that point, or are we a long way off?
Yeah, I think, well, certainly Louise Slaughter and others in the Congress have not only helped GINA, but have organizations like PGED come in and give briefings every few months in DC, and I think there's some interest in getting education. This is like the kind of education we needed when suddenly the internet came, and everybody thought, oh, we don't need to listen to computer geeks. It's like who would ever want to have a mainframe in their pocket, right? But we suddenly needed education, but that was not life and death. That was like the convenience of having a supercomputer in your pocket. But now we're talking about things that could really influence the quality of your life for your whole family.
It feels like we are drinking from a fire hose, and I know that 2 years ago you published a book, Regenesis, How Synthetic Biology Will Reinvent Nature and Ourselves. Yeah. Do you feel like that book is already dated 2 years out?
Well, it was dated enough that we brought out a paperback version of it with a significant update. And now the paperback's a little out of date, but it's not too bad. My guess is parts of it will last I hope will last a long time, and parts of it will look ridiculous soon.
What is the thing that's on your desk right now that you're most excited about?
Well, the malaria we already talked about. Gene therapy we didn't touch on, but gene therapy has come back from the dead. It got a little. There was a little premature action over a decade ago, where it wasn't mature and ready, and so. Can
you explain it for us?
So gene therapy ranges from fixing the rare diseases that we talked about that have a genetic component, essentially by reversing them, by putting in a copy of the gene that's missing.
Like Tay-Sachs.
Right. So in principle, you could, if you get it at the right stage in development, you can reverse things that cause blindness, that cause blood disorders, and so forth. And that can be either you put in a gene that covers for a missing gene, or you can fix a gene that's part of a process that could be fairly normal version of that gene or some hyperactive version of that gene, and there you want to take it out. So rather than put it in, you want to take it out. But those are the two kind of forms of gene therapy, knock-ins and knockouts. And they suddenly are working again, right? I mean, so the early days, we just didn't have the technology. It wasn't really ready for clinical practice. But now there are about 2,000 clinical trials using gene therapy in phase 1, 2, and 3, and some are already being approved. So, for example, Glybera was approved in Europe for pancreatitis, lipid disorder. So what you're seeing is great tolerance for genetic engineering for making drugs like erythropoietin and insulin and growth hormone, and even genetically modified humans in an environment where genetically modified foods are not approved, but all these things that impact health are. So I think that gene therapy could impact almost every aspect of health.
So if you're using these synthetic materials to recreate things, are you conflicted by that? What do we do about the human soul? Where does that come into play?
Well, we're typically modifying things that already exist. And if they already have a soul, like if I modify myself, through surgery or genetic surgery, then hopefully still has a soul.
That piece feels more tangible to me. Like I'm understanding that, but it's when we're starting from scratch.
Well, when
the creationism, that's sort of, I'm curious how you feel about that.
Well, I think that almost everybody that weighs in on this says there's at some point where life begins, right? Sperm and the egg are alive in a certain sense. They fertilize, they make an embryo. It's still alive. It gets more and more complicated, and it gets more and more alive, more and more sentient. Eventually it goes to school and makes more sperm and egg. And at some point it's always alive. It's always human. It's just that at certain points it's more sentient than at other points. The synthetic biology, the synthesis from scratch is just beginning. What we really do, more than synthesis by scratch, and in fact it's more useful, is modification. So in other words, you modify a cell to make it do something new. So,
but the capability could be there to start something from scratch.
It could be there, but you'd have to ask.
You have to think about it at some point.
You'd have to ask, why do it from scratch? I mean, we're coming pretty close to making a bacterial cell from scratch that has a new genetic code, and the reason is, the reason you're doing it helps you inform whether you're crossing some line. And so the reason we're doing it is to make a cell that's resistant to all viruses. By changing the genetic code, you can make it so the viruses coming in and say, whoop, what happened to the genetic code? It's all messed up. And then they not only can't live, they can't reproduce, they can't even mutate and become resistant the way a virus would if you gave a new drug or something in the wild.
I mean, I don't understand biology at that level to be able to know this. So does that mean that the virus could then go and become a super virus, or you're saying it would just bounce off and
you've created a super cell that is resistant to viruses. In principle, you could make a superorganism. You can make, agricultural species, plants and animals that are resistant to viruses. You might be able to make human cells that are resistant to viruses, but you haven't fundamentally changed it. Whether you've written it from scratch or whether you've modified it, the only thing that's different is the thing that you tried to change, and maybe some unintended consequences which you need to study. But it's really still the same living thing that you started with,
The sensational question for me to ask you right now is, do you believe in God? Are you playing God? Where does creationism fit in? But what I really want to know is, what public opinion do you want to change to help you innovate?
Well, some of the controversial topics that are either religious or almost religious in nature, that is to say, even things like global warming and genetically modified foods become religious in that they stop listening to the facts.
Right.
Or they stop having the facts as their top priority. They may listen to them on the hopes that maybe someday they'll agree with them, but they're not really actively participating in the experiments that could prove whether GMOs are safe or not, or whether global warming is an immediate threat or a distant threat.
Right.
And I think in some of these cases that gets solved with time. In other words, Galileo eventually was completely accepted by the same religion that rejected him.
Right.
And that just means, and in science, we reject things and that turn out to be right, and then we eventually accept them. It's just the time constant is a little different. But if something is truly valuable for society, if they can see, Galileo's version of astronomy was eventually valuable in terms of celestial navigation and longitude and all that stuff, and you get a more accurate physics. If evolution in the lab becomes valuable and we can make really big changes via lab evolution, then if you work in an evolutionary lab, you might accept evolution is a real thing, because you do it with your own hands and you can see that it's true. But until then, there's more heat than light. I mean, if it doesn't really matter to society whether evolution is true or not, why does it have to be the top agenda item for education? I mean, there's so much that students have to understand, so many concepts, not facts, but concepts, way to manipulate facts. Teach them the scientific method. Teach them how to be skeptical of statistics. Teach them how to make public policy decisions and corporate decisions based on fact-based method. But the fact-based method is very, very hard to apply to astrophysics and to ancient evolution. So start with things they can apply it to in everyday life.
Which brings us back to your personal genetic project. So everybody can access it.
Personal genomics is something that's extremely accessible. You can prove whether a particular food has an effect or not, whether a particular microbe is present or not, whether you're sending your kid to daycare with a allergy or with H1N1 or with Ebola, right? It makes a difference, right? And so just say, oh, kid has a fever, maybe it's nothing. Kid has some sniffles, maybe it's an allergy. You want to have the facts, right? And this is something where you can get the facts. It's much harder to get the facts about, whether, what something happened prebiotically, or when the first cell crawled up on the land. But determining whether your kid has a disease that's contagious or not is well within our capability.
So, Captain George Church, if I'm going to take your boat to the New World, how do I give and people listening and reading this genome to the Personal Genomics Project? How do I get involved?
So if you're interested in
signing up
and learning more about it and deciding whether it's for you and your family, personalgenomes.org, or just Google personal genomes and it'll pretty much up there near the top, and it'll lay it out for you, and you can sign up. And
am I sending you my spit? Am I coming to?
Well, so we do spit for some things. We mostly use blood. It's a higher quality genome. We also sometimes use skin if we're establishing stem cell lines. But we have blood drives in a certain sense in multiple cities. And we also need money. I mean, this is not, we provide it as a free service, but ultimately somebody has, it's all funded. We have a lot of volunteers that work on the project, as well as, of course, the volunteers that donate blood. And we have some rich friends that occasionally give us a little money. But it's extremely, I mean, we could scale this up much faster and much more, help a lot more people if more people would contribute.
I'm wrapping up the interview, but I have to tell you, I think you're lucky to be an early adopter. Do you realize that?
I love being an early adopter. It has its downsides. You will try things out that may not be good for you, or may not, mostly don't work. But yeah, it's the benefits definitely outweigh the risks and the downsides.
George Church, I'll be excited to hear what your next big breakthrough is, and it might just be Nova smiling or rolling over, but right. I hope you'll let us sit down with you again, because I think there'll be a lot more to talk about as we keep going.
Okay.
Thanks so much.
Thank you.